I'm John Lyles, a New Mexico caver and a member of the Fort Stanton Cave Study Project. I'm going to talk about a UHF cave data communication network for Fort Stanton Cave that's in development now. And the Fort Stanton Cave Study Project, in collaboration with the Roswell Field Office of the Bureau of Land Management, is developing this distributed communication network for data, and it's a wireless mesh network. The goal is to establish quasi-real-time sensor network that'll measure air conditions such as temperature, air movement, air direction, CO2 content when the flooding is going on and there's degassing, and also measure similar water conditions in the intermittent Snowy River stream channel from the closest point at Turtle Junction, where Snowy River is accessed, back to the surface and to a nearby facility a few miles away. That's about a 2-mile trip in the cave from Turtle Junction back to the surface. Then the passage dimensions vary from giant walking trunk to low crawls and includes muddy floors, pools, hills, small valleys, several gates, and many bends that can affect the signals. We chose 915 megahertz as the band as opposed to 2.45 gigahertz, which is another option, because 915 megahertz has a better potential for range, as well as the size of the wavelength being fairly small and still being able to propagate through most of the passage dimensions without attenuation, excessive attenuation due to the waveguide effects. The data throughput is not a critical spec in this system. It won't transmit video and fast real-time data. Power consumption and reliability are the most important criterion, so we're going to focus on those aspects, and data rate may be on the order of 10 megabits per second, 10 kilobits per second, which is fairly slow, but should be adequate for the sensors that are being read every so many minutes. The mesh network will work for redundancy, but initially it'll be a fairly sparse network with not a lot of cross-linking, and we'll be doing a point-to-point test. Ultimately, if you add enough modules to the network, you will have redundancy, because if one unit fails, the network will reroute automatically and use the other radios. But the radios, that means you almost have to have two radios inside of each other, which starts to run up the cost as well as complexity of this, putting them in the cave on both sides of the passage, for instance. The 2020 goal is just to have it to 20 steps, which is less than a mile from the entrance, if we can make it work. We'll first start out with a demo system with about 3 units to see how it works in the cave and see how far we can spread these units out. This map shows from the entrance on the left to 20 steps, and I put little boxes which indicate the radios. Those are actually the little modules, and those are straight line distances, so I believe we will be able to make those links with that many units. It's about 10 units, but we could find out that we need more. And like I said, that's a very sparse network. If we want to have more redundancy for full mesh, we would add more units in there. But going on from 20 steps to Turtle Junction, you can see it gets more complex. The northern passage above 20 steps starts getting into water, and then at the point where it goes to Turtle Junction, it turns to the east. We get into some low crawls. We go through a gate. We're going to have some kind of mechanism to have 2 radios on each side of the gate, and maybe have wires going through to carry the Ethernet connection through, and then retransmit on each side. The three-year goal is to try to get this thing to work to Turtle Junction. The BLM has funded us to work on this thing, so this is kind of an exciting project because the hardware is paid for. The labor, of course, is volunteer. The ZigBee protocol is what I've chosen initially after looking at LoRaN and other LoRa, and other techniques that are used in wireless data transfer. ZigBee has been around for years. There's a lot of companies making modules, and the only disadvantage of ZigBee itself is it uses one coordinator unit, many router units, and then end devices. So there's 3 different kinds of units in the network, and it also requires that the units remain active, which means continuous power, and that could be up to 50 milliamps on receive, so it's not going to work. So we looked at the options, and by the way, you can see here what a ZigBee network would typically look like, with a coordinator in the middle of the network that sort of tells which radios are on, and everything is active, and that handles the traffic going through in terms of managing the whole network. Didja Mesh is a more specific protocol that was built on the same kinds of radios that work in ZigBee, and Digi International developed this one, and it actually is an improvement, I think, because all the modules are identical, including the end modules, and it's adopted by a few manufacturers, so it's not as widely available, and so you have to buy from like Digi International or a few others. It is optimal for battery power though, because it runs very low duty factor, and it goes into a sleep mode and only draws 2.5 microamps, which is basically the leakage current of a battery. They call it asynchronous sleep mode. There is synchronous sleep mode as well. Asynchronous is where each unit has its own clock and they wake up at the same time, and you have to develop some overlap in your timing so that as they drift over the years, you can always make sure that they're all on at the same time and there's some overlap to be able to get the data through. Eventually, if they drift enough, you'll have to go in and recalibrate the network and take a laptop in and reset the clocks on them. And we don't know how accurate that's going to be based on crystal oscillators in these radios. So that's another thing to find out because of temperature change. Temperature is fairly constant, but it's going to be cold, and there's moisture and everything. These things are going to be mounted in boxes. I'll talk about that later. Because Didja Mesh has a larger frame size and a simpler address and header data, it means there's a little bit higher throughput of the data compared to ZigBee. And the next slide is a comparison table of ZigBee and Didja Mesh. And I'm not going to spend a lot on this. You can stop the presentation and try to read the text if you can see it. But it pretty much goes over what I said. Didja Mesh does not allow over-the-air automatic firmware updates. You would have to go in with a laptop or a tablet, connect to the units with the USB, and then update the firmware if needed. It has long range options, which is good, but we're not looking for long range between the radios. We're only looking for 100 meters or less between each hop. This is what the radio looks like. It's an XB is the trade name for this model from Digi, the XB-SX. It's a 900 megahertz module. I think there are 50 channels in there that you can select from, and it's frequency hopping, so you could have multiple units in one area that aren't interfering with each other. It uses Gaussian FSK modulation, which is an efficient modulation method with low intersymbol interference problems. It has a low data rate of 10 kilobits per second up to 330 feet in clear space. If you crank up the data rate, the range drops way down because the receiver sensitivity goes down. But in this low data rate, it has negative 113 dBm sensitivity. And the power consumption is moderate. It's 40 milliamps on receive, 55 milliamps on transmit. And that's when you're at plus 13 dBm. If you can turn it down, it'll go down a little bit. But I think we're going to probably need the plus 13 dBm to get these links, get the signal to hop between these links. And it's 3.3 volt DC, so there'll have to be a power converter in the box. It's a very small module, as you can see here. The box will be something like this that'll be sealed and have a nice gasket and clamped cover. It will have some desiccant inside. It will have the radio and a large battery, most likely a lithium ion, but we're not sure yet. I have to study the types of batteries that can last a long time with low self-discharge, because really it's not much of an advantage to have rechargeable batteries. We're going to have to take them out and put new ones in. We're not going to have time to take them out, recharge them, and put them back in. So we could use primary batteries even if they have long life. And there'll be a quarter wave monopole antenna on the top of the box, most likely. They'll have to be sealed. We hope to make it an annual battery change based on the calculations and the power consumption. And we'll have to balance duty factor of the awake time against the consumption. If we have a lot of sensors sending data, we're going to try to concentrate them all so that it'll work in synchronism with the first module at the turtle junction. And that module will actually be talking to a small computer, such as in Raspberry Pi or some other type of computer that someone's going to have to develop to collect the data from the different sensors and put it in packets. There's an application from Didja called XCTU that you use with a tablet or a laptop. It'll work in Mac and Windows, and you can use that to program and test the radios. It comes free, and there's these inexpensive development kits available from multiple companies like Mouser and DigiKey that'll include 3 of the radios and a little base unit with a USB port so that you can program them using XCTU. They also have standard AT communication commands like the old modems had, but I think it would be better to use the screen-based XCTU application. Here's how you calculate the range. Transmit power minus receiver sensitivity plus antenna gain has to exceed the path loss. And the path loss is the real question in caves. None of this equipment was ever designed to put in caves. It's made for on the surface between equipment, such as in refineries where you're looking at some valve or pump sending the information to a central collector. And now we're talking about putting in an area that has a lot different reflections and losses and no sunlight to recharge batteries. So it's a little bit of a stretch to make this work. And that's why I've chosen the XB with the Didja Mesh technology protocol right now. So the transmitter's plus 13 dBm, the receiver's minus 113, so minus a minus makes it a plus, and the antenna gain being a monopole is around 0 dB, maybe plus 1. So you get about 126 dB of transmission path. Then your loss, if it was free space outside, the calculations say it would be about 41 dB for, say, an 80 to 150 foot path. But in the tunnels, it looks more like 70 to 80 dB at 915 megahertz with a 100 meter path, according to one of the references, which I've included at the end of this talk. I think it'll be higher than that because we're going to have water, mud, bends and hills, and there's going to be some reflections and some absorption from the walls, so it'll probably be higher than that, but it looks like we should be able to at least get this 50 to 150 feet, or I'm not sure we'd get 100 meters, but I'm hoping we can. Prototype test is going to be necessary to determine the spacing. That's just not going to be something we can calculate and put it in and it'll work. We're going to have to bring in the radios and move them along, and I'll have a spectrum analyzer, a portable unit that I have, and we'll look at the signal levels and we'll adjust until we get a good location for them. Because this cave is open to or will be open to the public in the future, we're going to have to hide these things a little bit. They can't just be sitting right beside the trail. They'll be up on hills and rocks and things. And there'll be 2 gates. There's a main gate in the cave, and then there's one at Roaring Hill, which goes to the Don Sawyer Memorial Hall, which leads to a metal door that goes on to Turtle Junction. So I should have said there's 3 gates. And the 2 of the gates will probably polarize the signal, so it'll have some polarization as it goes through those gates because they're bat-friendly gates. The third gate is a metal door, and so we're going to have some method to get the signal past that. At the surface, the Bureau of Land Management is planning to build a small shed in the future with solar PV charging and a battery for some light in there, and it should be able to power the last module of the Didja Mesh network and feed a gateway module that'll connect to LTE using a directional antenna. So we'll be able to tie into the cellular data network. The data collection for the sensors will need a separate development of a small single board computer and power source, and that also will have to be a low power system, and when it's at Turtle Junction, and that will feed the first XB module there. So this is an example of what some antennas for LTE might look like. The one on the left is what I use on my house for a cell phone booster. The one on the right is a very high gain Yagi, which I don't think we're going to need in this case at Fort Stanton because it's near a highway and there is cell data there. And then the bottom one is a small cell phone booster that might work. So both the National Conservation Area, which is what Snowy River is included in Fort Stanton Cave, it's a congressionally mandated National Conservation Area. The headquarters for that, which is at Fort Stanton, and the FSC RP Fieldhouse will be able to access the real-time data using LTE through modem or cell phones or whatever. We'll know the flooding status of Snowy River year-round, even during bat hibernaculum closures, which are every winter. We'll have scientific payloads that can be monitored and near real-time without needing to download loggers in the cave. And eventually we may be able to add voice over IP or some kind of Bluetooth interface to a terminal device such as a smartphone to allow communication from Turtle Junction to the surface. But this could challenge the battery life, and the duty factor may cause a lot of delays in using it for voice. So this is just an optional feature in the future that we might look at. But right now the main purpose is just for data and from sensor payloads. So here's some references, and you can stop the presentation and look at these. Most of them are available online that explain a lot about wireless mesh networking and also some of the other Internet of Things systems that are around. A lot of them take a lot more development than this particular system, which is sort of off-the-shelf modules that you get running and then they start transmitting. Here's some good references on underground communications using UHF, VHF, and microwaves. And these high frequencies are a real challenge compared to low frequency cave radio, which is using magnetic fields and going through the earth long distances. So these are good references. Look them up, and especially like the second from the last one from the IEEE Antennas and Propagation magazine. That particular reference is pretty easy to read and has some nice charts of attenuation versus frequency for a lot of the IoT bands.